This is lesson 5 of chapter 4. In this lesson we'll talk about something called electron configuration. Now this essentially is a way of showing how electrons are stacked or arranged in the atom. So here is an example of an electron configuration, and you'll see a bunch of big numbers, a bunch of letters, a bunch of subscripts. We'll describe in a minute what this means, but the idea here is we fill the lowest to highest energy levels. So you have the nucleus of the atom, and then you have the different energy levels, and then we'll start filling the energy levels by first putting electrons on the lower one, then on the higher one, then the higher and higher and higher. Now this was the Bohr model of doing it, the visual way of doing it. Here we're going to represent the official way of doing it, and that's writing out letters and numbers, and this will show us how electrons are stacked. So here is what the diagram means. The big number is called the shell, also known as the energy level. So this is kind of the biggest the biggest breakdown of the atom, or the biggest way we break it down, the biggest category. And then the letter here is the subshell, also known as the sublevel. Remember, shells are broken down into subshells. And then the little number, the superscript, is actually how many electrons are inside that subshell. So in this case, in the p subshell, there are 5 electrons. And the big way of saying this is that the 2p subshell has 5 electrons. And then this is how we will fill out our electron configurations. So let's show you an example of this. Here's an example, and we're asked which atom does this configuration represent. So before teaching you how to fill these up, in this case, because these numbers represent the electrons, all we have to do is total them up. So you have 2 plus 2, which is 4, plus 6, which is 10, so far 10, plus 2, which is 12, plus 6, which is 18, plus 2, which is 20. So we have a total of 20 electrons in this configuration. 20 electrons correspond to which atom? Now remember, the atoms are arranged by their atomic number, and the atom that has a 20 above it is calcium. This number represents the number of protons, but it also represents the number of electrons, because all atoms are neutral. So in fact, this represents calcium. So do the same thing on your own in this practice problem. Tell me which atom this configuration represents. And then here is how we will use the periodic table to draw these electron configurations. The periodic table is the most important tool in doing this. So I've broken the periodic table down into what are called blocks. We have 4 blocks. We have the S block here, we have the P block here, the D block, and then the F block down below. Now, the way this works is that if we say have to fill up one of these elements, here's calcium, the one we've just seen. If we have to fill up calcium, what we'll have to do is we'll have to go from the beginning, which is the first shell, and we'll go this way and fill up all the elements, and fill these up, fill these up, fill these up, until we get to calcium, and we'll stop at calcium. So in other words, we're beginning at the lowest end inside the nucleus, or not inside the nucleus, but very close to the nucleus, and then as we go out, we're filling the atom with these electrons. And the periodic table is arranged perfectly to show you this. Now, a few things to see here. The S subshell is 2 elements wide, so you'll see that the S subshell, the letter S, will have a total of 2 electrons. The P subshell is 6 elements wide, so you'll see that P has a 6 on top. The D here is 10 elements wide, so you'll see that the D will have a 10 in the superscript, and the F, if you count, is 14 elements wide. It'll have F14. These are the maximum number of electrons that each of these subshells can hold. So you'll never go above 10 if you're in the D block. You'll never have P7 or P8 if you're in the P block. And these blocks, again, represent the subshells. And then we talked about subshells, and the more we do this, the more this will make sense. So don't worry too much if it's a bit confusing at this point. But here's what we'll do. We will actually fill up the 1s subshell, Then we'll fill up the 2s subshell, then the 2p subshell, then the 3s, 3p, and then the 4s as we get, for example, to calcium. So we're going to do another element here, so let's do that example, and it'll make more sense as we're doing this. The question is, what is the electron configuration of sodium? So we'll have to write from the beginning the whole configuration of sodium. The first thing to do is to find sodium, and I'm actually going to refer to the periodic table that you have, which is this, and sodium is found right here. Sodium is element number 11, so it has 11 electrons. So we'll have to make sure that we fill it up with 11 electrons. Refer to your periodic table as we're doing this. I know the quality on this may be a bit hard to see, but your periodic table should be nice and clear. So what we'll do is we'll always begin at the beginning. This number will show you the shell number. In fact, there are 7 shells, 2, 3, 4, 5, 6, 7 shells possible. So we'll begin at the first shell, and remember this is the S subshell, so we'll do 1s, and the S subshell holds 2 electrons. You can think of helium, which is pictured at the right, as being right next to hydrogen. The reason helium is placed on the right is because helium's properties match better on the right side along with all the rest of these. As you'll see, the periodic table is arranged to put them with similar properties in the columns. So we have 1, 2. So we have 1s2. Then we go down to the second shell. We'll put a 2. Again, we're in the S subshell, and we have 1, 2. So we'll put a 2. After this, we're going to go to the P subshell. Now the P subshell, remember, has a total of 6. This is the P subshell for a total of 6 possible electrons. Now the 2 here shows us the energy level of the P. So we'll put 2P and then 1, 2, 3, 4, 5, 6. 2P6 for the configuration. And then on to the 3 shell, shell number 3. For sodium has only 1 electron. We're actually going to stop at the 1. We will not put 2 because that will make us go beyond sodium to magnesium. So this is the electron configuration of sodium. 1s2, 2s2, 2p6, 3s1. And we are complete. Let's do another one of these, and you'll essentially have to practice a bunch in order to get this down. So why don't we do the same thing for the element zirconium. Let me also refer back to the periodic table and go ahead and do it on here. But as we're taking a look at the periodic table, let's find zirconium. The element zirconium is found right here. So essentially what we'll have to do is we'll have to go from the beginning all the way through the periodic table until we get to zirconium. So here it will be zirconium's electron configuration. Zirconium has 40 electrons. And we can actually count at the end whether our number 40 matches. Let's begin at the very beginning with 1s2. You'll see that all of these configurations begin the same. So we have 1s2. Remember, helium is right here. Then we go on to 2s2. Then we go on to 2p6. Then we're down to 3s2. Then we go down to 3p6. After that, we're down to 4s2, because remember, this is still the S block. So 4s2. Now after this, we get into the D block. Remember, this is the D block, and the D block has a total of 10 electrons, if you count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to go all the way through the D block, so we'll have a D10 at the end of it. Now, the number that goes before the D will not be the 4. It'll actually be 3. On the previous slide, we saw that D had an n-1 next to it. And I didn't explain it, but this means the energy level, which is represented by n, has to decrease by 1 for the D. And that's because we have not yet filled the D for the third shell. We have to first fill the D for the third shell. If this is confusing, just memorize it. This is the way it is. So this will actually be 3D10, not 4D10. But for the P, we go back to the 4. So this will actually be 4P6. And then on down to 5S2. And we're getting a bit crowded here. And then we'll end up with 2 electrons in the D, but in this case it'll be 1 less. and that is 4d2. So we'll end up here with 4d2 for the configuration. Again, look at this, study it. Essentially what we're doing is we're going through all the energy levels previous until we'll fill everything up to zirconium. Now, if you were to total these up, we've got 2, 4, 10, 12, 18, 20, 30, 36, 38, 40. Exactly what we see on the periodic table, 40 electrons. So your number of electrons in the configuration should match the total number from the periodic table. So let me quickly show you, if you go back just a few slides, let me show you this n-1 idea. So what I mean here is the D block, you have to decrease the energy level by 1. So this is actually the 3D, as you see here. This is the 4D versus the S is 1 more. The S is 1 more. The P is 1 more as well. Now when you go to the F block, it's n-2, which means, remember that this, if you take a look at the periodic table, this fits right in here. So on the S and on the P, you're on the 6th shell, but on the D, you're on the 5th. On the F, you're on the 4th. That's why it's n-2. 6 minus 2 gives you the 4F, is the idea. So hopefully this makes a little more sense. Go ahead and try this on your own. Try the example problem here. And then let's review one last concept. And this is going to be a way of writing the configuration a little more compressed, a little less extended. So this is called the noble gas notation. And you would write the noble gas that comes before the element in brackets, and we'll show you what the noble gases are. And then do represent part of the inner configuration, and after that, we'll put the rest of the configuration. So the example here is this. We have the example of what we've seen before of the calcium, and calcium having this configuration can actually be shortened. What you do is you take the noble gas, which is argon, that comes before calcium, and you put it in brackets, and whatever comes after argon will be the, you know what, I'll probably have to cut this up. Let's cut this up a little bit, because we will be out of time.